So we have a mass on a spring bouncing up and down, and we want to consider the nature of that motion. And you may recall from last year that first of all we have a situation where we have Hooke's law. So the restoring force is proportional to the deformation and opposed to the deformation, but that we can write this force as mass times acceleration, and perhaps you recognize that right here we have the second derivative of position. So you have a differential equation. This is actually a second degree differential equation, and I don't know if you have to do a double integral when you solve a second degree differential equation, but I like to do it by the method of known forms, or whatever it's called. And it turns out that a solution to this second degree equation is this, not the only solution, but this is a solution with these new variables introduced here. Let us convince ourselves that it is a solution to the differential equation describing this motion of a mass on a spring. And before we get any further, that somebody who obeys Hooke's law is called a simple harmonic oscillator, or we have simple harmonic motion that we are dealing with. So we are working out the differential equation to describe the motion of a simple harmonic oscillator, any mass that has elastic forces acting on it. If this were a solution, then taking the derivative with respect to time of this, here I hope that you got a chain rule to deal with, that the derivative of cosine is negative sine, but you also need to take the derivative of what's inside, so it ends up being xm, which is going to mean the maximum displacement times the cosine of omega t. And if you take the derivative of that, that is the second derivative of position with respect to time, we do get the derivative of sine is again cosine, so that negative sticks around, and then you have to take the derivative of what's inside, which contributes another omega, and we end up with this omega squared here. If we then take this value and put it in for omega squared, for this expression here, and this value here, and put it in for x there, we end up with this equation, negative x max omega squared cos omega t. I've moved the m over to the other side, so I have minus k over m, and then for x I put in x max cos omega t. And you can see it's looking pretty good. If I draw some lines through things, we'll make them blue lines, that here you have cos omega t, and here you have cos omega t, here you have x max, and here you have x max. So, and you got a minus here, and a minus here. So everything's looking good for this equation to be true, if indeed, oh, you turned into an arrow, you bum, that omega squared is equal to km, which we will work with later. But this omega looks like angular velocity. Instead, in this instance, we call it angular frequency, and it has to do with the rate at which this bounces up and down. There is a frequency that it bounces, but then you have its angular frequency, and let me go ahead and put that down, that the frequency with which it bounces is equal to the angular frequency divided by 2 pi. if you take the frequency, that is cycles per second, that is complete circles per second, and then multiply it by 2 pi, you get something that's rather like radians per second. Oh, look at that little teeny c. But we don't call it angular velocity. Its units are not radians per second. They are just per seconds, or its units, identical to the units of frequency, except frequency we might call cycles per second, and this is just per seconds. But this is this new entity, angular frequency, omega. Please do try to be careful to distinguish between angular frequency and frequency. They are two things, and if a problem asks for frequency, give them frequency. If it wants angular frequency, give them angular frequency. Okay, so here you have the solution to the differential equation that arises for a mass being acted on by elastic forces, and we also get the fact that the angular frequency, and hence the frequency with which it bounces, depends only on the springiness. This k was the spring constant, and the inertia. And that is a very unique result, that the way this bounces is completely determined by what mass you've put here and how elastic the spring is. Often, we were talking about the angular frequency as opposed to angular velocity, like an object going in a circle, and there is something useful to comparing uniform circular motion with the bouncing of a spring, and I'll show you a video of this as well when we get back to class. But the projection of this object going at uniform rate around a circle, if we project it onto the x-axis, then you have that the x position of this dot, which projected on the x-axis, is going to go back and forth, and we would like to assert that that projection onto the x-axis moves exactly the same way that this mass on a spring does. Well, if we're talking about the x value, how far out this is, then that's equal to the radius of the circle times the cosine of whatever angle you're at this moment. Or we can, instead of radius, we could call that x max, and instead of theta, we could call it omega theta, where this would be angular velocity this time. And then if we want to talk about the velocity that it has projected onto the x-axis, that's going to be its velocity. Notice it is going in a negative direction, and we're going to take the cosine of 90 minus theta to get the velocity projected here. But I can replace v by omega r and cos 90 minus theta by sine theta, so you end up with this result. And I hope if you compare that with the results we had in the previous thing, here's velocity is equal to this, and acceleration equal to that. Notice how similarly the results are coming out here. And then if we then take the derivative, well, if we look at the acceleration, which is here, and the projection of that acceleration, and the acceleration after all is v squared over r, or omega squared r, but it's going to be that acceleration times the cosine of theta would be a projection onto the x-axis. So here you have it. It is going in the negative direction, and the result we get is that the acceleration of this thing projected onto the x-axis has this result, which is identical to the description of the position, velocity, and acceleration of this thing bouncing back and forth. We are not trying to say that simple harmonic motion is equivalent to circular motion, or even that it is equivalent to the projection of circular. Well, maybe we are, but they are not the same thing, but you get the same result if you project a circle onto the axis, which makes us feel a little bit better about using these symbols, which seem to be for rotational motion in the case of something that's moving linearly along a straight line. Okay, I want to examine this, and now I've made it a little bit more general, the solution to the differential equation that we had. I've added in this phi, which is called a phase constant. I'll write that for you. Phase. The phase constant, and after all, if we were to take the derivative of this, we would end up with a negative sign, this quantity here, but then when we did the chain rule and took the derivative of what's inside, this is a constant, so it's not going to appear to mess up what's out front. This is the description of a simple harmonic oscillator. It is sinusoidal, and here you have it, that the phase constant would be where you are in the cycle at time 0. So if we put in a 0 here, this thing, we're getting a negative max, so we're taking the cosine of negative 90 degrees, or negative pi halves, I think, and so this phase constant for this particular motion here would be negative 90, or negative pi halves. That just a sense of what's going on with this equation. If you make xm bigger, what is that doing? And the people respond, you are making the amplitude bigger, so this curve would just come to look like this. It would still continue with the same angular frequency and the same phase constant. Let's get rid of that. If you made omega increase, well, what that means is if omega went from 1 to 2, suppose omega had been 1 and we increased it to 2, what it would mean is that for this to go through a complete cycle, to get up to 2 pi, would take half as long. That to go through a complete cycle with omega equal to 1, time would have to go up to 2 pi, or by 2 pi. But if omega was equal to 2, it would get through a full cycle in just pi seconds. So you have made the period, by making omega bigger, 1, you have made the frequency bigger. But in terms of this graph, what we need to recognize is that you have made the period smaller. That in fact, doubling omega would make the period half as long, the time for a complete cycle. And so what would happen if you doubled omega is this would get through a cycle. Here's a complete cycle from here to there, and it would do it in half the time. So our graph would then look like, see, I want to be back here, would look like this, that it would get through 2 periods in the time before it took to get through 1 period. That this would be increase in the frequency. And finally, if you were to increase phi, and this is the one that always messes me up, but what do we want to do? One, if you increased phi, suppose you took it from the current value, the cosine of no, that was wrong. The cosine, to get a -1, you need to take the cosine of 180, or pi. So currently, this phase constant is a pi, and so when t is equal to 0, we're taking the cosine of pi, which is -1. Excellent, times the x max. If we were to increase this, suppose we increase it all the way to, well, yeah, let's increase it to 2 pi. Then this starting position is going to be a +1. But the question is, did this point move back to there, or did this point on the sinusoidal curve come forward? So the other analysis you can do here, instead of looking at what it's like at time 0, would be to say, okay, to get through, to complete the first cycle, if we make this bigger, then this whole expression here is going to get to 2 pi sooner, and that is, less time will pass before it gets. So in fact, what happens when you make phi bigger, the phase constant bigger, is this curve goes back that way. And that always seems counterintuitive to me, that it backs up when you increase the phase constant. But it just gets to all the places it was getting to at an earlier time. So it does back up when you make this constant here bigger. Here's a sample problem that kind of weirded me out the first time I ran into it, so I'd like to hold your hand virtually. They give you that where the position of this, it is a simple harmonic oscillator, and its position at time 0, its velocity at time 0, and its acceleration at time 0 are given by this. And then they say, what is the angular frequency of the system, and so on. And it's like, whoa, where do you get started with that? But the fact that it is a simple harmonic oscillator means that we have this set of equations, that here is the solution for the position at any time, and the velocity, and the acceleration. So we would put in a 0 for t, and put this value in for x, and let's see, put in a 0 for t, and that value for x, and what do we got? Minus 0.0085 is equal to x max, which I don't know, times the cosine of phi. And similarly, we can put in this negative 0.92 for v, and that's going to be x max times omega. The omega's out there, times the sine of phi, and then this one here, and this is the winner. The acceleration is 47, is equal to negative x max, which I still don't know, omega squared, and again the cosine of phi. And the first question they asked was the angular frequency, which is omega, and you can see if you take the first equation and the last equation that I could divide this equation into this equation, and the x maxes would go and the cos phis would go, and I'd have omega squared is equal to something. I could solve for omega. As far as the phase constant, how do we get the phase constant? Perhaps that's here in my secrets to pull in. Okay, so that's what we just did. And then what I could do is take this first one and divide it into the second one, or the negative Why do you have a negative there? I don't think that belongs there. I could divide this one into this one, and again the x maxes would divide out. I'd be left with an omega, but I know what omega is equal to now. Let me write this out. I would have v divided by x, and the x maxes would go. We would still have that minus left over from there, and we would have an omega, and then I'd have tan phi. Dividing the first equation into the second, and I have numbers to put here and here. I've done the first part, so I now know omega. Thus I've got numbers everywhere but for that phi, and I could move this over here and take the inverse tangent of that to find out phi, the phase constant. And finally, to get the amplitude, I could, now that I know the phase constant, I could put that in and take the cosine of it, and I could solve for xm. Isn't that tricky? I hope you agree. Here's a checkpoint, and I'd like you to do it. It's not a big challenge. Please note that capital T standing for the period, it's at negative x max at time 0, so this does describe the positions at various times, this sinusoidal curve. When t is equal to 2t, not 0, but 2t, that is 2 periods later, what will x be equal to? Boom, choose, and then do this problem. 3.5 periods later, what will x be equal to? If at time 0 x is equal to negative x max, and at 5.25 periods later, what will x be equal to? And another checkpoint. They do say it's a simple harmonic oscillation, so you have all of those equations we've talked about, and they want to know which one of these would give rise to a simple harmonic oscillation. So here's the relationship between force and position. 4 different choices. Which ones would give rise, if you had that force behaving that way, which ones would give rise to simple harmonic motion? And it's a question of what kind of behavior gives rise to simple harmonic motion. And then finally, a problem of Mr. Houghton's that probably wouldn't trouble you, but it troubles me, that I can see this thing on a frictionless plate bouncing back and forth, and the only forces you've got is the force from the spring, and you get simple harmonic oscillation. But what about when it's hanging vertically? And this time you do not have the normal force canceling the gravity. Vertically you would have both the force from the spring and the gravitational forces. And so the question is, gravity pulling constantly down, does it cause it to go further below equilibrium than it goes above equilibrium? And maybe you never worried about that. The answer is no, it doesn't, but I had to prove it to myself, and you are going to suffer through it. Here is one proof. I will also share with you when we get back to class a modeling of it. But here is a spring with a mass on it, and here is the mass is bouncing up and down. This would be where the end of the spring would be if it was had no force acting on it. So it is deformed a little bit at this point in time. It's deformed by an amount y, but it's bouncing up and down between these 2 points. And there is the equilibrium point, and the question is capital X the same size as lowercase x? Does it bounce as far below as it bounces above? And the approach I took to working this out was to consider energy. I, after all, cannot work with my dynamics formulas because we do not have constant force. So this is probably the only way to attack this problem. And I have the energy when it's here at the top, which would be made up of both gravitational potential and elastic potential, and when it's at the bottom. And I will define that as the zero height, and so I will say it has no gravitational potential at the bottom and the only elastic potential. The gravitational would be mg times how high up it is, this x plus capital X. The elastic would be how much it has stretched the spring, that y. And there, the elastic, when it's down here at the bottom, it would have stretched it by y and also x and also little x. All of those together would be the deformation of the spring when it's down at this position. And when it's at equilibrium, the spring constant times the deformation should be equal to the weight of the object. Okay, so we take this expression here, and I'm going to replace mg by that expression. So for mg I put in k times the sum of y and capital X times lowercase x and capital X plus plus. And then we go through the laborious task of distributing here and foiling here. And you'll have to trust me that you do get these 4 terms out of this, plus this one is equal to, and you have these, how many? 6 terms over here from expanding the square. But look at this. Here we have 1/2 k times 2 little x big X, and that's going to be equal to k little x big X, and over on this side we have k little x big X. So those are going to take one another out. And here we have k capital X squared, and oh, come on, we need some more. Okay, here is 1/2 k y squared, and here is 1/2 k y squared. So those two go. More. Here is ky. Yeah, here we go. kyx, and 1/2 k times 2yx gets you a kyx there. So those two go. And is that it? Yes. I think that's all the pieces I can get rid of. Then what I'm left with is, oh, poot on you. What I'm left with is, here I've got a kx squared, and over here I've got a 1/2 k little x squared, and then I'll subtract this from this. This becomes a kxy, and here's a, oh, those ones went too. Let's go back to crossing off. kxy and a 1/2 k times 2xy. Yes, those two went. And so I'm left with, this is the only thing I'm left on that side, and these two expressions left over here. And then I can take this 1/2 k capital X squared and subtract it from that. I get this expression, and you can see that the solution to this is that little x is equal to big X. That it does go as much above as below. And you probably never even cared, but now you're done with that. Thank you.